The product that was chosen in this project is an aircraft wingtip, composed of carbon fiber reinforced polymer, CFRP. The wingtip is an aerodynamic and structural component in the outermost end of a plane wing. Its key roles are to cut down drag, enhance air movements, and enhance fuel economy. Hence, the wingtip is a safety-based aerospace component, which must be produced correctly and in a constant quality. The aircraft wingtip has been chosen in this project since it has a clear demonstration of the connection between the material choice, the manufacturing procedure, and automation. The wingtip has an intricate aerodynamic form which requires a high precision and repeatability. Automated production enables the production to have a control on shape and quality, which is desirable in good aerodynamic performance. The wingtip of the CFRP is designed to be used in an automated assembly line due to its properties and design. CFRP is used with automated operations, including automated cutting, robotic layup, vacuum bagging, CNC machining, and surface finishing. Besides that, CFRP wingtips are also lightweight, meaning that they can be handled with robots or automated vehicles.
In Assignment 1, a comprehensive material analysis was conducted to identify the most suitable material for manufacturing the aircraft wingtip. The analysis focused on the functional requirements, operating environment, mechanical properties, manufacturability, service life and cost considerations of the wingtip component. The wingtip is a critical aerodynamic structure located at the outermost section of the aircraft wing. During operation, it is continuously subjected to bending loads, torsional stresses, aerodynamic pressure, vibration, and cyclic fatigue generated by lift forces. In addition, wingtips are exposed to harsh environmental conditions, such as ultraviolet radiation, moisture, rain, low temperatures at high altitude and chemical exposure from de-icing fluids. These demanding conditions require the selected material to maintain structural integrity and dimensional stability over a long service life. Based on these requirements, 3 candidate materials were evaluated: aluminum alloy, glass fiber reinforced polymer, GFRP, and carbon fiber reinforced polymer, CFRP. Aluminum alloys have been traditionally used in aircraft structures due to its low density, good machinability and relatively low cost. However, its limited fatigue resistance and susceptibility to crack propagation under cyclic loading make it less suitable for modern high-performance wingtip applications. GFRP offers good corrosion resistance and lower manufacturing costs, but its lower stiffness and strength restrict its use to non-critical or lightly loaded structures. Among the evaluated materials, CFRP demonstrated the best overall performance. Based on the findings from Assignment 1, carbon fiber reinforced polymer, CFRP, is confirmed as the final selected material for the wingtip structure. CFRP is a high-performance composite material composed of carbon fibers embedded within an epoxy resin matrix. One of the most important advantages of CFRP is its exceptionally high strength-to-weight ratio. By using CFRP, the overall wing mass can be reduced, contributing to improved fuel efficiency, enhanced aerodynamic performance and reduced operational costs. In addition, CFRP exhibits excellent fatigue resistance and is inherently corrosion resistant. From a manufacturing perspective, CFRP is highly suitable for aerospace applications due to its compatibility with advanced and automated production techniques. CFRP wingtips are typically designed as integrated composite structures, and the reduced part count makes CFRP wingtips highly suitable for automated assembly environments. Therefore, carbon fiber reinforced polymer, CFRP, is the most appropriate material choice for this project. Main operation is most important stage in making the wingtip. In this stage, raw material is transformed into a high-strength load-bearing structure. The process begins with the mold preparation using precision tools, usually a CNC machine mold made from aluminum materials. This mold is the exact negative of the final wingtip shape. Into the mold, technicians carefully place carbon fiber prepreg, which are cut using automated ply cutting systems to achieve accurate geometry and correct fiber orientation. The materials such as Nomex honeycomb need to be added to the product to reduce weight and keep strength. After completing the layup, the assembly is sealed in the vacuum bagging system. Vacuum is applied to remove the trapped air, consolidate from the laminate and ensure uniform resin distribution across the composite layers. The last step for the main process is autoclave curing. Once it is cured, the laminate becomes a rigid and fully consolidated structure that cannot be reshaped. The next stage is secondary operation that elevates cured CFRP wingtips from mold form into a qualified and ready aerospace component. The next step is CNC machining, where processed on a high-precision 5-axis milling machine. Contour milling is performed to meet strict tolerances in hole position, aerodynamic profiles and attachment interfaces. Assembly and packaging operation phase represent the final process in the manufacturing wingtip. The first step in this stage is the component assembly. Component assembly is the process of integrating all necessary function elements in the wingtip. Technicians need to follow the engineering drawing to install additional parts such as metal brackets, navigation light, static discharge wicks and access panels in wingtip with high precision. It will use 2 primary joining methods, which are mechanical fastening and structural adhesive bonding. Furthermore, the next step is final inspection, which is a final quality gate and data closure point before product release. The final step in this operation is protective packaging. This professional packaging establishes to protect the wingtip from climatic hazard to ensure the wingtip arrival at the destination is in perfect condition. The assembly line is designed at a conceptual level. This means it focuses on the process flow and the arrangement of workstations, rather than exact machine size or factory layout. A linear, one-direction flow is applied, where the wingtip moves forward step by step without backtracking. In total, the conceptual assembly line consists of 8 main processes. These 8 processes are arranged sequentially along the assembly line, as shown in the layout diagram, to clearly illustrate the overall production flow from the first manufacturing stage to the final packaging stage. The first workstation in the assembly line is the carbon fiber layup station. This station, carbon fiber prepreg layers are placed into a mold according to the required fiber orientation. This process forms the main shape and structural foundation of the wingtip. After layup, the wingtip moves to the vacuum bagging station. Vacuum pressure is applied to remove trapped air and compact the composite layers before curing. This step helps improve laminate quality and ensures uniform consolidation. Next, the wingtip is transferred to the autoclave curing station. Controlled heat and pressure are applied to cure the epoxy resin and permanently bond the carbon fibers. This process gives the CFRP wingtip its final strength and stiffness. After curing, the wingtip is moved to the demolding and trimming station. The cured part is carefully removed from the mold and excess material is trimmed. This prepares the wingtip for precision machining in the next stage. The next workstation is the CNC machining station. Here, CNC machines are used to drill holes and machine edges with high accuracy. This ensures the wingtip meets dimensional and assembly requirements. After machining, the wingtip enters the surface finishing station. Sanding and protective coating are applied to improve surface smoothness and protect the CFRP structure from environmental damage. The component assembly station is located near the end of the assembly line. Additional components such as brackets, fasteners, and functional parts are installed onto the wingtip. This completes the functional assembly of the product. Finally, the wingtip is transferred to the inspection and packaging station. Quality checks are carried out to ensure the wingtip meets all specifications. Approved wingtips are then packaged using protective materials for safe transportation. In conclusion, this conceptual assembly line layout demonstrates a clear and logical process flow. The linear arrangement of workstations supports efficient operation and is suitable for small-scale automated manufacturing.
Question 1. If a CFRP wingtip has internal defects but passes external inspection, should it be rejected? Why? Question 2. If the aircraft mainly operates short-haul flights instead of long-haul flights, is CFRP still the best material choice for the wingtips? Why or why not?